In this last part of Lecture 2, we will explore sedimentary depositional environments and structures and what clues they give us about Earth history. An environment of deposition, or a sedimentary environment, is a geographic setting where sediment is accumulating, such as a river, a delta, or a continental or oceanic basin. The environment of deposition determines the nature of the sediments that accumulate: grain size, grain shape, composition, etc. There are three broad categories of sedimentary depositional environments: continental, marine, and transitional. Continental environments include the following three types of erosional and depositional environments. Continental environments are dominated by stream erosion and deposition. Streams are the dominant agent of landscape alteration on Earth. Glacial deposits are typically unsorted mixtures of sediments that range from clay to boulder size, and wind or aeolian deposits are well-sorted fine sediments. Marine environments are divided into two categories: shallow marine environments to about 200 meters of depth border the world's continents and receive huge quantities of terrestrial sediments. Warm, shallow seas with minimal terrestrial sediments will have carbonate-rich muds. Deep marine environments, those that are seaward of the continental shelves, have primarily fine sediments that accumulate on the ocean floor, with the exception of turbidity currents. Transitional environments include the shoreline as the transition zone between marine and continental environments. Examples of transitional environments include beaches, tidal flats, lagoons, and deltas. This slide shows you photos of different depositional environments and points to where they are located on a general diagram. From top left moving to the right, you can see the continental environments, which include caves, sand dunes, lakes, alluvial fans, glacial deposits, swamps, rivers, and even landslides. The transitional environments include beaches, tidal flats, sandbars, and deltas, while the marine environments include deep and shallow marine environments, including coral reefs. Different sediments often accumulate in adjacent environments at the same time. These contemporary adjacent sediment units are called facies. Each unit, or facies, possesses a distinctive set of characteristics reflecting the conditions of a particular environment. Transitions between different facies are typically gradual. In this diagram, you can see a set of basic marine facies. All of these rock types are forming adjacent to one another at the same time, but at different water depths. So, for example, while you have sandstones forming on a beach, you have limestone forming at the same time in a deeper marine environment. Marine transgression is a landward movement of sea, also called an onlap sequence. It is a rise in sea level. A marine regression is a seaward movement of water, also called an offlap sequence. It is a drop in sea level. The illustration on the right relates the rock facies we would find in a vertical sequence of rocks related to a regression and a transgression. The transitional environment rocks are always in the middle. The transgression will have marine rocks on the top and continental rocks on the bottom because sea level is rising onto land. A regression, when sea level is retreating from land, would be an opposite sequence. This illustration shows an example of a vertical sequence with a facies change diagram. The top is a marine transgression, which creates a fining upward sequence. That means that the rocks on the bottom are coarse and they get finer as they move up in a vertical sequence. A regression, such as the one on the right, creates a coarsening upward sequence as the sea level drops. The brick pattern is a fine grained limestone. The pattern with lines is a shale, which is coarser than limestone, and the pattern with the dots is sandstone, which is the coarsest rock type represented here. Sedimentary structures provide additional information useful in the interpretation of Earth's history. The layers of the sedimentary rocks are called strata or beds. They're the most characteristic structure of sedimentary rocks. Bedding planes are the separation between strata. This image shows the strata that are characteristic of sedimentary rocks. Cross-bedding occurs when the layers in the sedimentary rock are inclined. These structures are characteristic of sand dunes, deltas, and some stream deposits. Cross-bedding structures tell us the flow direction of the energy in the environment, whether it is wind or water energy. The top of the crossbed is inclined toward the direction that flow is coming from. In these photos, you can see a cutaway section of a modern sand dune showing crossbedding, and in the large photo, you can see fossilized sand dunes preserved with their crossbeds intact. This allows us to determine the direction of the wind when these dunes were initially deposited. Graded beds are a unique situation where the sediments in strata gradually change from coarse at the bottom to fine at the top. This structure is often associated with turbidity currents and alluvial fans. Turbidity currents are a density-driven current of sediment that flows down submarine canyons into deep marine environments. As soon as the sediment flows out of the canyon and the velocity drops, the larger, heavier particles settle to the bottom, followed by the medium, and then the fine particles. This creates graded bedding structures. This photo shows normal graded bedding that fines upward. You can see the change in particle size from the bottom to the top. Other sedimentary structures that tell us about the environment of deposition include ripple marks, which are small waves that are lithified in the sedimentary rock. Mud cracks, which indicate sediments that formed in alternately wet and dry environments, and fossils, which are the remains of prehistoric life. If ripple marks are created in an environment with a constant back and forth energy, like the ones on the top, they will be symmetrical, indicating an environment like a beach or a large lake. Asymmetrical ripples, like those on the bottom, indicate a unidirectional energy flow like that of a river. The bottom photo shows ripple marks. The top left are mud cracks, and the top center and right are fossils, one marine and the other terrestrial. So you can see we can determine a lot about the environment of deposition through these sedimentary structures. One last thing we need to discuss is the carbon cycle and sedimentary rocks. The carbon cycle is a biogeochemical cycle on Earth. Carbon dioxide is one of the most active parts of the carbon cycle. Plants absorb carbon dioxide through photosynthesis. When plants die, some of the carbon dioxide is deposited in the sediments. Over geologic time, considerable amounts of plant biomass is converted into fossil fuels. When fossil fuels are burned, that carbon dioxide is released back into the atmosphere. Marine invertebrates build shells out of calcium carbonate, which locks away carbon dioxide in limestone when these animals die and their shells sink to the bottom of the sea. When limestone is quarried and crushed for various industrial purposes, some of that carbon dioxide is released again. Fossil fuels and limestone are just two of the carbon sinks on Earth in the sedimentary rock record that help to equalize the carbon dioxide in the environment. This is a very basic carbon cycle. There are three main sources and sinks: the land, ocean, and atmosphere. Take some time to study the interactions between the three sources. This is the end of Lecture 2. In our next lecture, we will explore geologic time, the time scale, and fossil preservation.